Hey, what's up everybody? In this section of this course, we're going to go over the binary search pattern. To explain what binary search is, I think it's important to first explain what linear or sequential search is so that we can better understand the advantages of using one over the other. So for linear or sequential search, let's imagine that we have an array that looks like this. Let's also imagine that we want to determine if this value exists in the array. The linear approach would be to iterate through every element of our array until we either reach the end of the array or we find the target value within the array. As you can imagine, searching every element of the array like this would, in the worst case, take O of n time. That is, our algorithm's time complexity will scale proportional to the size of n. That's simple enough, right? Good. So now, with that in mind, let's move on to binary search. Now it's important to note that for binary search to be applicable, there's a precondition we must meet. The data structure, in this case the array, that we are searching must be sorted. You'll see why this is the case soon, but for now let's consider an array that looks like this. Let's imagine that we want to find this value within this sorted array. The way binary search works is, we first find the middle value or midpoint of our array, and once we've found the midpoint, we compare it to the value that we're trying to find. Since our array in this case is sorted in ascending order, any value that is greater than our middle value is going to be on the right side of our array, and any value that is less than our middle value is going to be on the left side of our array. And yeah, you guessed it, this means that we can determine which side of the array our target value is on by checking to see if it is greater than or less than our midpoint. And of course, if it's equal to our midpoint, then we've found our value, but that's not the case just yet. So our target in this case is greater than our midpoint. And as you can see, any value that is greater than our midpoint will be on the right side of our array starting from the midpoint. So this means that we can now completely do away with the entire left side of our array, including the midpoint. So as you can see, compared to linear search where we would need to check every element on the left and right side of our array, being able to do away with an entire side in the case of binary search is very powerful. And there's more. We'll be able to do the same thing we just did when we check the right side of our array for our target as well. We'll first find the midpoint, then cut our search area in half once again, with our new search side being determined by checking to see if our midpoint is greater than or less than our target. Eventually, our target will be our midpoint, or if our target doesn't exist within the array, it will just never be found. So compared to linear search, the time complexity of a binary search algorithm would be logarithmic or O of log n. I'll go into detail regarding time and space complexity later, but for now, it's only important that you understand how binary search is actually working. So moving on, does all of this mean that binary search is a superior algorithm to linear or sequential search? Well, not necessarily. As with most complex things, which algorithm to use depends on many factors. The most obvious one being that binary search can only be used on sorted data structures. Linear or sequential search can be used on both sorted and unsorted data structures. So with all things being equal, if we were given an unsorted array and asked to find a target value, to use binary search we would first need to sort the array. So let's, for the sake of example, say that we sorted the array using merge sort. That call to merge sort takes O of n log n time. And following that, we'd find the target value using binary search, which would result in O of n log n plus log n total time, which we can just simplify to O of n log n. But either way, linear search can find the target value in O of n time, which is in this case more efficient. So it's important not to get into the mindset of saying or thinking that one algorithm is better than the other. In computer science, it's almost always situational. Now before we get into writing some code, I should mention that there are both recursive and iterative algorithms for binary search. We're going to go over both, starting with the iterative approach, and I'm going to contradict the previous statement that I made just now about getting out of the mindset of saying that one algorithm is better than the other and say that in most, if not all cases, the iterative binary search algorithm is better than the recursive algorithm. That's because with all things being equal, aka they are both relatively easy to implement, the recursive algorithm uses O of log n space, while the iterative algorithm only uses O of 1 space. Anyways, feel free to pose your arguments to the contrary in the comments section, and feel free to post your own binary search algorithms in your favorite languages in the comments section as well. In my opinion, it's always great to see how different minds approach problems. Anyways, without further delay, let's get into writing some code. Okay, so to start within our Python source coding interview patterns directory, we're going to make a directory called binary search. And then we'll change directory into that directory, and we're going to make a directory called binary search again, because that's the name of the problem that we're going to be solving. And we can change directory into there, and we can go ahead and start up a virtual environment. And from there we can start with our iterative binary search solution. So we can just create a file called binary search iterative.py, and within that file we're just going to define binary search. And it's going to take in a nums array and a target. And for binary search, we're actually going to make use of our 2 pointers pattern as well. So we'll start with a start pointer, which is going to be the first index of the array. And then we'll create an end pointer as well, which is going to be the last index of our nums array. And from there, we can just go ahead and start a while loop. And we're going to loop while start is less than or equal to end. And at the beginning of this loop, we're going to get our midpoint by essentially calculating the average of the start and the end index. So we'll do start plus end, and we'll divide that by 2. And from there, all we want to do is we want to check to see if our midpoint value is equal to our target. Because if that's the case, then we've found our target within our array, and we can just return mid, which is the index of the target. But if that's not the case, we are going to check to see if our mid value is less than our target, or our target is greater than our mid value. And if our target's greater than our mid value, that means that the target is on the right side of our array. So that means we're going to do away with the left side of the array. And the way that we're going to do that is by changing our start value to the mid value plus 1. So we're essentially cutting off anything up until the midpoint of the array, including the midpoint. And our new search area at that point would be the right side of the array. But if the opposite is the case, so if nums mid is greater than our target, then that means that our target is less than our mid value. So that means that our value is going to be on the left side of our array. So this time we would set our end equal to mid minus 1. So in this case, we're cutting off the right side of the array by setting the end of our array to the midpoint minus 1. So we're going to cut off the midpoint and everything after it as well. And that's pretty much it for the binary search algorithm. We're just going to return -1 if we don't ever find our value. And now we can just go ahead and get into creating our entry point. So if name equals main, we're just going to print the result of binary search, and we're going to pass in the array from the problem description. So we'll just pass in this array, and we'll pass in the target 9 as well. And the target 9. And we can go ahead and save, and we can run this file and see what happens. So the output that we get here is the index 4, which is the expected output. If we have a look at the problem description here, the expected output is 4. Index 4 is where the value 9 is contained. And now that we've created our iterative solution, we can go ahead and also create our recursive solution. So we'll do binary search recursive.py. And once we've created that file, we can just open that file up. And within this file, we're going to first create a wrapper function, which we're just going to call search. and it's going to take in our nums array and our target. And this wrapper function is just going to return the result of our binary search function. And the binary search function is going to take in nums, and it's going to take in our left pointer and the right pointer, which is going to be the first index of the nums array and the last index of the nums array, and it's going to take in the target. And then we can just go ahead and define another function called binary search, which is again going to take in nums, left, right, target. So for this recursive function, we're going to need to create a base case so that we don't recurse infinitely until we run out of memory. So we're going to do if start is greater than end, we're going to return -1. So if start becomes greater than end, that means that we never found the target value within our array. So we're just going to set our midpoint equal to start plus end divided by 2, similar to the last iterative solution. And similar as well, we're going to check if nums mid equals our target. And if it does, we're just going to return mid. And we're going to check to see if our target is greater than our value at mid. And if it is, we're going to recursively call our binary search function with our nums array and our mid being set to, or our start being set to mid plus 1, and our end being set to end and target. So this is the same thing that we did in the iterative solution. We're just passing our mid plus 1 as our start if our target is greater than our midpoint. Because if the target's greater than our value at the midpoint, then that means the target's on the right side of our array. So that means that we want to start our array after the midpoint. Starting from the midpoint to the end of the array is the right side of the array. And we'll also do if target is less than our value at mid. And if that's the case, we're just going to return binary search nums. And this time we're going to start our array at the original beginning, and we're going to end it at mid minus 1. And that's because if our target is less than the value at our midpoint, then that means our target is on the left side of our array. And if that's the case, we want our array to start from its original starting position, but we want it to end at the midpoint, minus the midpoint. We don't need the midpoint. And that's pretty much going to be it for this algorithm. So now we can go ahead and create our entry point again. Name equals name. And we're just going to print the result of search. Our wrapper function is what's calling our binary search function. So we need to print the result of our wrapper function. And we're going to pass in the same array from the problem description. And the target 9. And actually, let's clear this. And then we can do Python 3. Binary search recursive.py, and we get an invalid syntax error on line 2, so let's have a look at that. And I spelled return wrong. And let's try again, and we still have the same error, so let's see. Shouldn't put that there either. And everything is broken. Start is not defined. That's because I named it left and right in the actual function signature. Actually, let's keep it start and end, and we'll just change this to start and end. And hopefully that works. All right, good to go. So as you can see, for our binary search recursive algorithm, we get the result 4 as well, which is the index that's expected. So let's go ahead and get into the visualizations for both the iterative and recursive solutions. Okay, let's get into the visualization for our binary search iterative solution. And we're going to start with an array that looks like this. And we'll have a target that is 8. And this is so our visualization can depict a worst case scenario. And for binary search, we're going to make use of 2 pointers. And we'll call them start and end. And our starting pointer is going to start at index 0 of our array, and our end pointer is going to start at the last index of our array. And actually, let's move this down a little bit. And let's also add our indexes. So for our iterative solution, we're going to basically iterate through a while loop while start is less than or equal to end. So once start becomes greater than end, then we're going to terminate our while loop. And for each iteration of this while loop, we're going to recalculate the section of the array that we want to be searching. So for every iteration, I'll actually just write out which iteration that we're on. If we're to pass this array into this iterative binary search function and start at our 0th index with our end being the final index of the array, our first iteration of this while loop, we can just write out iteration 1. So within this first iteration, we're going to set our midpoint by dividing our start plus end index by 2. So our current starting index is 0 and our current end index is 7. And 7 plus 0 is 7, divided by 2 is 3.5. And we're just going to floor that to 3. And our midpoint is going to be the 3rd index of our array. So we can go ahead and draw this midpoint and move it to index 3. So within this first iteration, we're setting our mid to index 3. And we're going to check to see if our mid is our target or the value at mid is our target. And the value at mid is 4, which isn't our target. Our target is 8. So we'll move on to this line of code here where we're just going to check to see if our value at mid is less than our target, which it is because our value is 4 at mid and our target is 8. So that means that we're going to do this line of code here. We're going to set our start equal to mid plus 1. So our start is going to get moved to mid plus 1. And let's move our mid out of the way. So within this first iteration, we're setting our start equal to mid plus 1, which is index 4. So here start equals index 4. And then we move on to the next iteration of this while loop. So we'll just write here iteration 2. And once again, we're going to calculate our mid by adding our start plus our end and dividing the sum by 2. So our start index is 4 and our end is 7, which results in 11 divided by 2, which results in 5.5, which we will just floor to index 5. So our mid will move here to index 5. So within iteration 2, we set our mid to index 5. And then we check to see if our value at mid is equal to target. Our value at mid is 6, our target is 8, so this will not resolve to true. And then we check to see if our value at mid is less than our target, or if our target is greater than our value at mid. And our target is 8, and our value at mid is 6, so our target is greater than our value at mid. So that means that our target is going to be on the right side of our mid. So we're going to once again set our start equal to mid plus 1. So our start is going to move to mid plus 1. So within this second iteration, we set our start equal to mid plus 1, which is index 6. And let's just move this up a little bit. And now here we can write out iteration 3. Because after this code, of course, we don't do this one because this doesn't resolve to true. And then we go to another iteration of our while loop, which is this iteration here, iteration 3. And we calculate our mid once again. So start plus end, so 6 plus 7, divided by 2. So 13 divided by 2, which is 6.5, which we will just floor to 6. So for this, our midpoint will be equal to 6. So let's move this to index 6, which is the same index as our start. So within this third iteration, we set our mid equal to 6. And once again, we check to see if num's mid equals our target, and it does not. Our mid value is 7 and our target is 8. So once again, we end up at this line of code where we check to see if our target is greater than our mid value, which it is. So we set our start equal to mid plus 1. So we can move our start to mid plus 1. So now we have our end is at the last value and our start is at the last value. And let's move this over here. And this line will not resolve to true, so another iteration of this while loop, because our start is still less than or equal to end, because currently our start and end are equal. So we do another iteration of this while loop. And within this iteration, we need to once again calculate our mid. So we're going to add our starting index plus our end index divided by 2. And both our starting index and our ending index are both 7. So 7 plus 7 is 14, divided by 2 is 7 once again. So our mid's going to be 7 as well. So within our fourth iteration, we set our mid equal to 7, and then we're going to check to see if our value at mid equals target. And in this case, our value at mid does equal target, because the value at mid is this last item in our array, which is our target 8. So in that case, we'll return mid. So in this fourth iteration, we return mid. And that would be the end of this function. So now let's go ahead and get into time and space complexity, starting with time. So our time complexity is going to be O of log n, because O of log n really just means O of log base 2 n. And in this situation, our n is the size of this nums array, which is 1, 2, 3, 4, 5, 6, 7, 8 elements. So our n is equal to 8. And if we plug that in here, we get O log base 2 8, which equals 3, because 2 to the power of 3 equals 8. And what this 3 means is, for an input size of 8, or when n is equal to 8, this function is going to need to do O log base 2 of 8 work, which is 3, which is reflected here. This while loop does 1, 2, 3, 4 iterations. So in actuality, the time complexity of this function here is O log base 2 of 8 plus 1, because log base 2 of 8 is 3, plus 1 equals 4, which is the number of iterations that we had to do in this function. So this here, let me write it over here because I'm running out of space. O log base 2 of 8 plus 1 is O log n plus 1. But in big O, we ignore constants, so we can ignore this plus 1, which comes out to O log n, which is our time complexity for this function. And as for our space complexity, ironically, we don't need much space to write out what our space complexity is. We can just write it over here, because our space complexity is O of 1. And the reason our space complexity is O of 1 is because for this solution, we're not using any extra space at all. So the amount of space that we use for this solution is constant. And that is going to be it for our visualization of the binary search iterative approach. Okay, so let's get into our visualization for this binary search recursive implementation. So for our example array, we'll just use an ordered array that looks like this. We have 1, 2, 3, 4, 5, 6, 7, and 8. Should be simple enough. And then we'll have a target of 8 so that we can essentially show the outcome in a worst case scenario. And as we're visualizing this, when we draw out our binary search function, like when we draw it out here in our visualization, we're not going to draw out the nums array plus the first and last index of the array, etc. in the target. We're just going to draw out what the array would look like given these variables. So for example, there is going to be an initial call to our binary search function here. And what that's going to look like is we're just going to have binary search. And here in our arguments, we're not going to write out all of this. We're just going to write out what the array is going to look like initially. So initially, the array's start point is going to be the 0th index, and its end point is going to be the last index. So here we'll just draw out the entire array so that you guys can see what's happening visually. And let me just expand this a bit. So we can go ahead and draw out 1, 2, 3, 4, 5, 6, 7, 8. And that's what the array looks like as a whole, but of course we're using 2 pointers. So in reality, we're just working with the portion of the array that is defined by our start and end index. And what's going to happen is we're going to arrive at this first line of code here when we first pass in our initial array, and we're just going to check to see if start is greater than end. And currently our start is 0 and our end is 8, which is reflected in this visualization here. We're showing the entire array. So start is definitely not greater than end. So we're going to move on to calculating our mid, and let's just go ahead and write in our indexes here: 0, 1, 2, 3, 4, 5, 6, and 7. And let's move this down. And let's also draw out our start and our end. So currently our start is at index 0 and our end is at the last index of the array. And let's draw out our mid as well. And we're going to calculate our mid here. So we're going to add our start and our ending index and divide it by 2. So 0 plus 7 divided by 2. So 7 divided by 2 essentially, which is going to be 3.5, and we're just going to floor it to 3. So our middle index is going to be index 3. So we can go ahead and move our mid to index 3. So this is our initial call to binary search. The portion of the array that we're searching looks like this because our start and our end are like so, and our mid is this index here. So then we would move down to here and we check to see if our mid is equal to target. So the value at mid is 4 here, and our target is 8, and 4 is not equal to 8, so this condition does not resolve to true. And then we'd go down here to check to see if our target is greater than our mid value. So if our target is greater than our mid value, then our target's going to be on the right side of the array. And if our target is less than our mid value, then it's going to be on the left side of our array, because our array is in ascending order. So it goes from lowest value to highest value. So in this case, our target is greater than our middle value. So that means that our target has to be on the right side of our array. So what we're going to do is we're going to return another call to binary search, this time starting our start index at mid plus 1. So we're going to move our starting index to mid plus 1, which means that we're now only searching this part of the array because our start is here and our end is here. And we can move our mid for now. And we can go ahead and draw out this next call to binary search. And again, we'll draw out the array. But remember, essentially, we're drawing out the portion of the array that we're searching. We're not drawing out the actual array. So we're going to draw out 5, 6, 7, and 8. And this is just for visualization purposes so that you guys can visualize this, because our starting index and our ending index goes from 5 to 8. So that's what we're drawing out here in this call here. And once again, we end up at our base condition to check to see if start is greater than end. Start is still not greater than end. So we'll move on to calculating our mid once again. And our mid is going to be the index 4 plus the index 7. Or the index 4 plus the index 7 divided by 2. So 4 plus 7 is 11, divided by 2 is 5.5, which will just floor to 5. So our mid is going to be index 5. So we can go ahead and move our mid to index 5. And once again, we want to check to see if our mid value is equal to target. Our mid value is 6 and our target's 8, so they are not equal. So then once again, we'll go down here. And we're going to again check to see if our target is greater than our mid. Our mid is 6, our target is 8, so our target is indeed greater than our mid. So that means that we need to continue to search the right side of our array. So we're going to return another call to binary search with our starting point being mid plus 1 once again. And as you can see here, we're setting our start to mid plus 1 because at this point, we already know that our target isn't equal to our midpoint value because we checked that here. So we can just completely skip over the midpoint value and set our target equal to mid plus 1. So let's get the mid out of the way for now. And this is the portion of the array that we're working with currently. And we're once again making another call to binary search recursively. So we'll do another recursive call, binary search. And this time our array from a visual perspective looks like this. So we once again end up here and our start is still not greater than our end because our starting index is 6 and our ending index is 7. So we'd go down here and calculate our mid once again. So we're going to add 6 and 7 and divide it by 2, which is going to mean 13 divided by 2. And 13 divided by 2 is 6.5, but again we're going to floor that 6.5, so it's just going to be index 6 where our mid's going to end up. So we can go ahead and move our mid to index 6. And then we'll check to see if our mid equals target. So does 7 equal target? No. So we're going to move down to this line of code again. And once again, our target is greater than our mid value. So that means we need to continue to search the right side of the array. So we're going to once again return a call to binary search, a recursive call, and we're going to set our starting point equal to mid plus 1. So right now, let's move the mid for a second. And our starting point is going to move to mid plus 1. And I apologize for the noise. It just started raining really hard, but we'll just go ahead and finish this. And this is going to be another recursive call to binary search. And this time, our start and our ending index are both here. So the array that we can visualize is going to just be an 8 here. So this is what the array is going to look like. And we can go ahead and move this mid out of the way. And in this call here, we're going to end up here again, and we're going to check if start is greater than end. And start's still not greater than end. Start and end are equal at this point. So our mid is going to be starting index, which is 7, plus the ending index, which is 7. So 14 divided by 2, which results in 7 as well. So that means our midpoint is going to be the index that we're already on, 7. And at this point, we're going to check to see if our midpoint value, which is 8, is equal to our target, which is also 8. And at this point, we're going to return the midpoint value because it is equal to 8. We have found the target value. And this would be a worst case scenario for binary search. Another worst case scenario would be that the value doesn't exist within the array. So if the target value were 9, we'd still go all the way to this final recursive call here, searching for it, and we would never find it. Which brings us to our time and space complexity. So our time complexity in the worst case is going to be O of log n. And let's just go ahead and highlight this here as being our initial call. And these calls here are our subsequent calls, our recursive calls. And the reason that the time complexity for this is O of log n is because O of log n actually means O of log to log base 2n. And in this case, we can do O log base 2, and our in this case is the size of this array, and this array has a size of 8. So our in is 8, and I'm running out of room here, so let me try and move this up. So this here just means to get 8, what power do we need to raise 2 to? And the answer to this is 2 to the power of 3, because 2 times 2 times 2 equals 8. So that means that, sorry, I have to move this up again. That means that O of log base 2 of 8 is equal to 3. And as you can see here, for an input of this size, of size 8, we must make 3 recursive calls to binary search. So that's why binary search is O of log n. And as for our space complexity, maybe use a different color. So our space complexity is actually the same thing. It's O of log n, because in these same calls to binary search, each individual call is being added to the stack, taking up stack space. So the amount of space that we take up with this recursive implementation is going to be O of log n as well. I hope that makes sense. And that's going to be it for this portion of this course. If this has been helpful to you, please don't forget to like, and if you haven't already, please subscribe, and I'll see you in the next one.